Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis using R software. And we're in chapter 10 part of this playlist, which I'm calling Cluster Analysis. And let's jump to today's topic, which is K-means clustering. Now, K-means clustering is considered a partitioning method that allows for observations to move from one cluster to another as needed. And as a reminder, in hierarchical clustering, once an observation has been assigned a cluster, it will not change. That's not like K-means clustering. As things update, distances change a little bit. So we're allowed to move observations back and forth between cluster. Now, to start a K-means clustering, you have to know how many clusters you want. So we have to pick K, how many clusters. And then we also have to do what's called seed it. We have to give it starting values in each of those clusters. So we have to pick K seeds to start these clusters. Now there's four common methods. We select K random observations that are at least a distance of R apart. Second method is select the first K observations that are at least a distance of R apart. We could select K observations that are mutually farthest apart and use those as our seeds, or in method, or 4 to pick seeds is we pick the K centroids from the K cluster solution from an average linkage hierarchical cluster method. And actually this is what we're going to highlight in the R programs. The other three are settings that you can just easily set. And so we'll highlight this fourth method to pick the seeds for your clusters. Now the K-means algorithm, then alternates between these next two steps until no further improvements are possible. So each point in the data set is assigned to a cluster with the nearest seed based on Euclidean distance. Now the cluster seeds are updated with centroids of the cluster, right? So initially we have to use the seeded values, but then once clusters get values, we do away with the seeds and we use the centroid of the cluster, which is the mean or the average. And then the centroids are then used hereafter in place of the cluster seeds. Then we repeat this step. Each point in the data set is assigned to a cluster with the nearest seed, with the nearest distance, smallest distance. Centroids are updated. We look at every object to see which cluster it's closest to, reassign it if necessary, and we just keep repeating this until there's no further improvements. And then that's our K-means clusters. Now let's illustrate this in R. And the data is from an FTP site, and we're looking at protein data, and it's really the consumption of protein by country. So we look at this 9-dimensional vector. So it's red meat, white meat, eggs, milk, fish, cereals, starchy foods, nuts, fruits and vegetables. And we want to cluster these observations based upon these variables. Now, country we assign to row names because it really makes the plotting look much prettier in what we're getting ready to do. Since country is not a continuous variable, we just get rid of it. So that's what we do here, reassign it to Y. Now, since we're going to use hierarchical clustering to generate the seeds for our K-means clustering, we need to run hclust and with method average, right? We feed it a distance matrix and we use method average, and we store all that information in HCAV. So it's hierarchical clustering average method. Now we're going to start with 4 clusters. So K equals 4. And now I want to plot the results from our hierarchical clustering. I want to highlight the 4 clusters using rec.hclust. And this is it. So this is the dendrogram from our hierarchical clustering method. And these are the 4 clusters that we get. So now what we want to do is calculate the average or the centroids of these vectors in each of these clusters. Now remember, these vectors are 9-dimensional vectors. So this is what we do. Let me make it one step bigger. So we use a function called cut tree. So the hierarchical clustering result, we say k equals, and I have a variable called 4. So we want to cut this tree so there's 4 clusters, store that information in temp. Then I run it through this crazy looking statement here to create a matrix of cluster means. Now I take those and put it in the k-means function. K-means is the workhorse that we're going to use. So our data is y. The centers, which are the seeds, we use these cluster means that we created from the hierarchical clustering, and we store it in k-class. Those are the results. Now we can just look at those results and see which observations are sorted into which clusters. We can do that. But I want to sort of visualize what happened, and one approach to visualizing the k-means clustering results is to use principal components. So we use principal components on our data y. So remember, those are 9-dimensional vectors. We grab the first 2 principal components, and then we color the dots based upon the clusters that we got from our k-means, and I picked different characters or points based upon the clusters that we received in our k-means clustering, and we print it. And this is the results. Now notice that the results are nicely grouped, right? They are kind of separated. But one thing to remember is we're taking a results that's in 9 dimensions and then shoving it down into 2 dimensions. So it's a representation of that 9-dimensional space in 2 dimensions. So it does the best that it can. But it looks like it did pretty good. Now I want to, if we just want to take the results from the k-means and look at the clusters, and I like to sort them. So it tells, this is all cluster 1, cluster 2, 3, and 4. Now let's repeat what we just did, but using 5 clusters. So k equals 5. I want to plot the hierarchical clustering using the method average. I want to create pretty little rectangles around it. So here are the 5 clusters using hierarchical clustering. 1, 2, 3, 4, 5. Notice Finland is by itself. It has its own cluster. And I point that out because the k-means will allow observations to move between clusters, and it's going to gain a couple observations after the k-means algorithm is used. So we use cut tree. So the object is this hierarchical clustering result object. We want to cut it using 5. Remember, I reassigned the variable k to equal 5. We store that information in temp. We run it through this crazy statement, which creates a matrix of cluster means. Now there's 5 rows in each with a cluster mean. And we put that as a center in the k-means function. So y is our data. Our centers are these cluster means from hierarchical clustering. We store it in k-class. Now we could just print out the clusters and see which observations are clustered, with what other observations. But again, I'm a visual person, so let's try to visualize that 9-dimensional clustering in 2 dimensions. We use principal components, same statements actually. And this is what we get. So here are the 5 groupings. Yep. Now notice that group 5 kind of overlaps with group 2. And one of the reasons is that we're taking 9 dimensions and shoving it into 2 dimensions. So there may be some overlap. Now, is 4 clusters better than 5 clusters? I don't know. There are things that you can do to evaluate. You look at the within cluster sums of squares versus the between sums of squares, uh, and you take the ratio of those and you can see which one's best. So there's ways to evaluate this. I'm just saying that it's tricky to evaluate it with a picture, from 9 dimensions shoved down into 2 dimensions. If we wanted to print the clusters from our our k-means method using 5 clusters, this is it. Now notice Finland, there's, now it's a cluster of 4 because these observations were allowed to move back and forth until it finished. And that's it. Okay, so I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.